So welcome back, everyone. Happy to follow up now on Philippe's lectures from yesterday, where we'll continue to talk in this little mini course on subconvexity in the broader context of this building bridges school on automorphic forms. So I guess as Philippe mentioned a bit, since it's a school in automorphic forms, we're kind of focusing mainly on techniques for bounding automorphic L functions. So having in mind the higher degree case where the degree is 2 or higher. So there are some things in this course that might normally appear in a broader course in analytic number theory, treating the subconvexity problem, such as the techniques specific to the zeta function or the Dirichlet L functions. So Philippe mentioned Weil's method and Burgess's method as examples of techniques that kind of are the genesis of the subject. And we're instead focusing here on the techniques that kind of apply to automorphic forms, so things on GL2 or higher. And so in that sense, this is kind of an incomplete course if it were a broader thing on subconvexity. But on the other hand, it's kind of nice because there aren't so many methods that we know of for bounding L functions in higher degree, depending upon how you think of method. So one method, which I'll spend most of the lecture talking about, is called the moment method, and this already showed up in Philippe's lecture, where you try to estimate an L function by estimating a moment that it contributes to. So this is for subconvexity on GL2 and higher. Okay, so beyond this method, I'm not sure if there's anything else that kind of continues the list. I don't actually know if there's really a 2 here. And I say I don't know because, of course, you can write a paper that implements the moment method in a way that doesn't obviously show a moment. And sometimes it takes work to actually kind of find the moment hidden in a method. So an example of a method that has seen a lot of success in recent decades is the delta method. And so it doesn't look like a moment method, but at least in some cases we can kind of understand it in those terms. So I'm not going to spend time today talking about this. Philippe already talked about it a bit yesterday. And I don't know, is there a 3 that we can put here for subconvexity and higher rank? I'm not sure if anyone knows of another example. Of course, it's always kind of risky to say that there are no examples of papers treating something by some method other than some short list, but okay. That's what I know of. Okay, so then kind of zooming in on 1, which will be our main focus. So the name of the game is to estimate a moment, which I guess I'll put big here. So we'll typically have some family that we call F. So F will be some family of things we can attach L functions to. And so maybe it's some family, for example, of automorphic forms or automorphic representations on some general linear group, so there's some degree involved. And typically we break these families down into ranges according to their analytic conductor. So the analytic conductor, let's say, is in some interval, maybe Q, 2Q, where Q is some parameter that we have tending off to infinity. And then, okay, we try to estimate something like this. And I mean, usually we want the things that we estimate here to be non-negative so that we can do the trick that Philippe already mentioned yesterday, where we bound an individual summand by the sum of all of the summands. Okay, and I guess one way to enforce that is to take absolute values everywhere. But then usually for this to have kind of a natural interpretation as an actual L function of the sort that we started with, we need to take an even power here. Because you can take an even power of an absolute value by multiplying together some integral copies of the original thing and then the same number of copies of the conjugate. And then of course you get a 2k over here. Okay. And so the expectation, which follows from the Lindelof hypothesis, is that each of these terms here has size pretty close to 1, where pretty close to 1 will mean maybe closer to 1 than any positive power of the conductor that we're letting grow. So you'd expect this to have size comparable to roughly the size of the family. So an example along such lines would be something like the conjectures for the integral moments of the zeta function. Okay, so here of course it's not a finite family that we're integrating over, but we think of it as something like a family of size t. So this also illustrates the point that I'll kind of generally write sums in places where one could also write integrals, and you kind of make the obvious modification. So this is at least conjectured to behave like some constant depending upon k times roughly t. And then there's an additional logarithmic factor that for our purposes won't matter so much. So this is a conjecture that's known for k equals 1 and 2. And so the fact that this conjecture, or what we know towards it, kind of peters out when k gets a bit big is kind of a general symptom whereby these moments become more difficult to estimate the larger that k gets. And that's kind of reasonable to suspect, because if you look at the upper bound that you get for an individual L function from assuming an estimate like that and taking an upper bound like so, what it tells you is that L of pi half is, let's say, roughly bounded by the family size to the 1 over 2k. So if we call that estimate star for the moment, this estimate that we say follows from GLH, but also follows from the weaker consequence given by this moment estimate. So when does star beat convexity? So we recall that convexity says that L of pi half is not much larger than q to the 1/4. So for that estimate to be better than that estimate, so what we need to have is that the family size to the 1 over 2k is, say, bounded by q to the 1/4, maybe minus delta, because we always care about saving an exponent rather than something smaller. Okay, and then another way you can write this, just, that might be convenient sometimes, is, you can think of this as saying the family size is at most q to the 2k all raised to the quarter minus delta. Okay, and the way we think of that is we stare at the thing that's being summed here, this L function to the 2kth power, and we think of attaching an analytic conductor to that power, that 2kth power. And conductors behave multiplicatively when we multiply L functions together. So that conductor would be q to the 2k. And the conclusion in general is just that the family size always needs to be a bit smaller than the fourth root of the conductor of the thing that we're summing over the family. So for instance, in this example that I highlighted here, you see that the family size is t, and the total conductor, well, typically, let's say for t kind of near its largest value, it'll be capital T to the 2k. And so the fourth root of that, the fourth root of the conductor will exceed the family size exactly in the two cases indicated here. In this case here is kind of right on the edge, meaning you kind of just barely fail to beat this bound that you'd like. Okay, so to kind of make this desired relationship hold, there are a couple things you can try varying. I mean, if we think of the conductor and pi as kind of given asymptotic parameters, the two things you can vary are the number k, which tells you how big of a moment you should take, and then the family f, which you're free to choose containing your given pi. And so to make this estimate more feasible, you can either make k bigger, which makes the right-hand side bigger, which is good if you want this to be satisfied. And of course, then you run into the trouble that the moments become harder to evaluate. And the other thing you can try to do is you can try to make the family smaller. So, you know, in the setting of this example, you could try replacing an interval like between 0 and t with a shorter interval, maybe containing numbers that are very close to t. Say differing from it by a power of t less than 1. Okay, and then, so the other technique that you can use for making this kind of moment method work when you're right on the edge is this amplification method that Philippe introduced in yesterday's lecture. So in this edge case, where the family size is comparable to the fourth root of the conductor, one can try using the amplification method. So this amounts to taking kind of the same moment, but inserting in here an amplifier. So where an amplifier is some so okay, I won't say exactly what L is, but it'll be some sum with some kind of arbitrary coefficients weighting some parameters, so say Hecke eigenvalues or coefficients attached to the thing's pi that you're summing over. So the idea here is that the CL are maybe general complex numbers, maybe assume they're bounded by 1 or something like that. And so you can choose them to amplify the contribution of a particular pi, which then makes your moment, so rather than look like, you know, so kind of a moment as above is an unweighted moment over some family containing the pi that you care about. And so you instead kind of modify that weighted moment to maybe be a bit smaller away from pi and a bit larger at pi. So you replace an unweighted moment with a weighted moment where the weights are kind of some positive power of the conductor. And it's kind of a proxy for considering a slightly larger moment. So it has a similar effect to what you'd achieve if you could say, for example, establish estimates like this with k equal to something like 2 plus epsilon. So namely, if you have a little bit of room in your method for evaluating a moment for kind of the threshold value of k, then you can try actually making that work by inserting an amplifier like this and then seeing if you can still get asymptotics. So when does this actually work in practice? Maybe before I try to address that question, I should just ask if there are any general questions on what we've said so far, what we reviewed, anything from yesterday. Sorry, you asked what is capital L? So capital L in practice will be something like Q to some very small parameter, maybe call it alpha or something like that. Yeah. Yeah, Q is a parameter that we just choose, but we might choose it exactly equal to the analytic conductor of pi. That's a reasonable choice. But I mean, kind of all that really matters is the size of Q. So Q is well defined up to a factor of 2 or something like that. So we just group all of the things that we're looking at by kind of the dyadic range to which their conductor belongs. I don't know if I'm still answering your question, but is that?
Yeah.
Okay. Cool. Okay. Yeah, anything else?
Actually, another notation.
Yeah, great.
I don't know what the 2 squiggles between the small L and the big L mean. What does that mean?
Yeah, good question. So this you could take to mean something like saying that like L lies in an interval between, let's say, capital L and 2 capital L. So that would be one way you could define it. But more generally, people would allow you to like replace this Q and this 2Q with like any positive fixed multiple of Q, like 1/10 Q and 10 times Q. So in other words, it says that the ratio kind of remains bounded away from 0 and infinity. How do you make sense of this summation here? Yeah, we could think of this as being something like little l is a natural number that lies between capital L and twice capital L. Something like that. Yeah, thanks. Anything else? And I should say the whole lecture, like kind of after this part, will be like about examples of this. So that's why I've kind of just given one example to start, but we'll give many more as we go. Okay. Yeah, so of course, you notice that when you're kind of like, okay, well, for example, presenting this material in a lecture, or for that matter, working it on your own on scratch paper, I mean, if you were actually to write the amplifier up there in that sum and then write the whole sum out, you'd be using a lot of chalk, and if you have to kind of repeat that expression a bunch of times, you know, it can become a bit burdensome. So something we often do when kind of working things out by hand or sketching things or presenting things is we want to not actually write the amplifier, but still kind of know in our hearts when we would be able to insert an amplifier. This is something that's kind of worth, I think, explaining just briefly. So, so this method, the amplification method, typically succeeds when one has a, so what I'll call robust asymptotic formula in the edge case. So what is meant by that is so okay, maybe we write it like this, and we normalize the moment by the size of the family so that the expected size is something comparable to 1, roughly. And so what I mean by kind of a robust asymptotic formula is one where you get a, well, okay, of course, a main term and some error term. So that's what's meant by an asymptotic formula. So here a main term should be something kind of the form maybe q to the little o of 1. So something that kind of, you know, okay, maybe it'll involve logarithms of q or something like that. An error term will be something that kind of looks like, so we'll want something like q to the negative delta, where delta is some fixed quantity. But okay, we want a bit more than this. We want the main term to be structured, which in practice doesn't have much content, but the idea is that like we should be able to understand how the main term varies in a very down-to-earth way if we vary the family in a very slight way. So if we perturb it a bit, we should have some kind of good grasp on this. And I don't think this is ever a serious restriction in practice, but it's kind of something that one needs to implement this. And then the other thing we need is that we need the error term to be kind of what I'll call robust, which means that it shouldn't kind of blow up in some uncontrolled way if we again perturb the family just a little bit. So what happens in such cases typically is you can insert an amplifier, and that has the effect of replacing this main term by some, let's say, negative power, maybe L to the negative beta, q to the little o of 1. And then replacing the error term here by maybe L to some capital power A, q to the negative delta. Where I guess so the feature of structure here is what lets you make this a bit smaller than it would otherwise be, and the robustness here is just asserting that you have some kind of polynomial control over how this thing blows up. And so we saw an example, like quite literally, of this form in Philippe's lecture where he kind of illustrated the amplification method. So I'll just refer you to look back at that to see that it indeed fits into this pattern. So when we're writing down an argument, we typically don't throw in the amplifier at each step. We just have in mind that this is our goal. We want to have some kind of structured main term, some robust error term. It should be much smaller, and it shouldn't blow up if we change things a bit. And in such cases, we can kind of trust by experience that we could convert our proof of that asymptotic formula into a proof involving an amplifier that would then do a bit better than we could in this edge case. Okay. Yeah, any questions about that before we continue?
So this is essentially a method of when we have the moment, how we can like use an amplifier to like just be able to tweak it and just get some, you know, some slight improvement over what we would get before. What is there like any? I mean, this is probably a really big question, but like, like how does one even come up with those moments, like these things for moments in the first place, or are we typically just taking something that exists in the literature and adjusting it, or like, or are we like?
So usually the whole challenge is to prove something like a moment asymptotic.
Yeah.
And so your question is, how do you think up which moments to consider, or how do you analyze the moments?
Right.
The second question, or maybe both questions.
Both questions.
Yeah, both questions,
Yeah.
okay.
I guess my question is just like, I don't know too much about the theory of moments
Yep.
in the first place, so like what's
Sure. So if we go beyond rank 2, there's not so much theory of moments in some sense. And by that I mean, most of the moments you'd naturally write down, nobody's written a paper kind of studying them in detail, and most of the questions are kind of wide open, and we don't have any good science for understanding exactly when we can or cannot understand moments. If we restrict to the zeta function or something like that, it's much better developed, but this is kind of an automorphic school, so it's a bit like the Wild West, if you know what I mean. Which is good mathematically, because it means there's a lot of stuff to figure out and kind of structure to find. So your guess is as good as mine. I mean, I'll give some examples, and I've thought about many examples, but whatever you feel like on a given Sunday, I'd say.
essentially the moments is the hard part of this process, is what you're saying?
Yeah, well, I would say the hard part is finding a method that actually allows you to evaluate a moment asymptotically in a case that is kind of relevant for subconvexity, where this bound holds. And I'll claim, or I'll kind of indicate in a bit, that there are basically 4 examples where we know how to do that in the literature. So it would be extremely exciting if anyone found a 5th example. It might completely blow up the subject and, you know, solve all the problems we've dreamed of. But yeah, good question, thank you. Yeah, any other question just on these generalities here? Okay, so maybe before I dive into the examples, I'll give just a couple indications of how one can, in principle, try to analyze one of these moments. And then the examples will consist of actually realizing these principles in a few cases. So, so how to evaluate a moment. So there are at least a couple basic ways you can try to do it. So maybe let's focus on the case when k is equal to 1. So in the above notation, this just says that we're just taking kind of the squared magnitude of something and summing it. And we can always kind of formally reduce to that case by treating the kth power of the L function as an L function in its own right. And so it's just a matter of kind of notation to reduce to that case. So in that case, so we have, so Philippe already mentioned, so one, I'll give it a title. So the title is Approximate Functional Equation plus, say, some summation formula. So this means you write down something like L of pi half. So So Philippe explained, I think, that you can write this as a sum over natural numbers of, so some coefficient divided by square root of n times some test function that truncates n to the range where it's of size up to about q to the half. So here v is a function that looks something like that, plus some other sum involving the root number that looks, I'll just say similar. So it'll involve a conjugate, but otherwise it'll have kind of a similar shape. And so for the purpose of understanding subconvexity, I mean something that's kind of baked into the general convexity bound, which is mentioned in our exercise handout, is that you can always kind of treat these coefficients as if they're basically bounded by 1 on average. So what you get from that is that only the largest range of n, the range where n is of size roughly q to the 1/2, is kind of relevant. So for subconvexity, it suffices to consider so a sum where n ranges over q to the 1/2, and sometimes we'll write the superscript smooth to denote that. So some of you guys have asked, like, what do we mean by n is of size q to the 1/2? This might mean that it's in an interval delimited by q to the 1/2 and twice q to the 1/2. And the superscript smooth means that we actually implement that truncation using some smooth test function. So we insert a factor like maybe v star of n over q to the 1/2, where this is v star. So it suffices to consider a sum like this, and you can also just kind of treat the sum on this other side in the same way. You can use the triangle inequality to get rid of the epsilon pi, which can be problematic if you want to study its variation. And so then, I guess I'm running out of Blackboard, but studying a sum over pi in a family f of L of pi half squared. So this kind of reduces in some sense to, well, you first need to understand sums over pi and f of lambda pi of m, lambda pi of n bar, where m and n are in some range comparable to q to the 1/2. And then there's a family of tools for doing so called Kuznetsov formulas or Peterson formulas, which in practice will give some kind of explicit formula for this sum, but maybe in terms of complicated objects like Bessel functions and Kloosterman sums. But then once you've applied that, you just have the game of actually analyzing those objects summed over m and finding asymptotic formulas for them. And then it's a whole kind of zoo of examples one can look at to see, where can you actually succeed in doing that. And we'll look at some of those shortly. Okay, so the other class of examples, so I just want to kind of continue this Blackboard over here. So I'll say there's another class of methods that involve something like applications of Parsifal's identity. So we'll again give like some concrete examples of this in the body of the lecture. Philippe already gave one example along such lines of this yesterday. So in Philippe's lecture, he had an example where if you take a modular form and you sum it over CM points attached to some imaginary quadratic field K, then this ends up equaling, up to some proportionality constants, the sum of over Idel class characters chi for K of L of F times, let's say, the theta function attached to K to chi at 1/2. So this is an application of Parseval identity because, I mean, what's really used in establishing this is that this L function itself is given up to proportionality by the sum of F twisted by chi summed over CM points for K. And so then it's Parseval's identity that links this, squared, thank you, yep. It's Parseval's identity that links this sum of squared kind of Fourier coefficients of F restricted suitably to this L2 norm of F. And so we'll see some other examples implementing this principle in the lecture. So when I say related, you know, I include in this things like the pretrace formula, which is kind of the, if you'd like, the mother of all ways to average automorphic forms and understand them, as well as literal applications of Parseval's identity, kind of like that. And so we have a couple different ways to try to like search for moments that we can actually estimate. So we can either start with whatever family we're interested in, just expand everything out in terms of sums like this, evaluate the sums using some form of the Kuznetsov formula, and then try to do anything we can. And I mean, this has the great advantage that it gives us some explicit thing to work with that we can stare at and play with. We got actual letters that represent integers that appear in our sums. We can numerically evaluate it if we'd like to see what is big and what is small. Okay, or we can dive into the theory of integral representations of L functions and search for an integral representation like this, and then see if that integral representation is amenable to some application of Parseval that we can actually do something with. So if you remember in this example, this turned out to be amenable because we knew by some other means that CM points equidistribute, which then allows us to get a handle on the left-hand side. But kind of the difficulty more broadly is that we might not know maybe the analog of CM point equidistribution or whatever we actually need to analyze the left-hand side that we get from some application of Parseval to some moment. And also the theory of integral representations of L functions is itself kind of vast, but there are lots of examples that are completely concrete where we don't know how to do some moment using them. Okay, and with that, I think we're ready to dive into some kind of overview of examples. But as before, I'll pause for questions, and I'm happy to see where we're doing. So this is extremely shorthand notation for, so you take F, which is like a modular form, and then you restrict it to the set of CM points. And okay, the set of CM points you can identify with ideal classes in some imaginary quadratic field, and you weight those ideal classes by chi, and then you sum over all the CM points. Does that address your question? Okay. Yep. All right, I'll start the board shuffle, but if there are any questions while I'm doing that, please interrupt. Yeah. So let's see. I mean, at least since they don't work simultaneously, there's less pressure on me to look like I'm doing it efficiently in a coordinated manner. So that's kind of nice. Because normally they'd be going in like the opposite direction all at the same time. Whereas here it looks like very organized, so good. There is this available, right? Oh, there's this one, yeah. Is this, Sorry, let me just do it properly, because this is a bit, you can think of questions while I do the proper erasure, right? All right, here's a question for you. What was your favorite moment from Philippe's lecture? Gosh, that's a tough question, right? It's like, because there are so many good ones to choose from. But does anyone want to venture a favorite? The second moment of what? All right. All right, so yeah, good. Isn't that nice? All right. So examples where we can. So I could write do this, meaning what we just described, but maybe to make it clearer, we can asymptotically evaluate what I'll call convexity critical moments. And so again, I'm just going to talk about GL2 and higher, since that's the focus of this week. Okay, so one would be the case where we do what? Maybe we fix pi on GL2. So think pi is like a classical modular form or the representation attached to it. And then we vary what I'll call sigma on GL1 So let's say in some I'll call it a dyadic family. And it'll be clear what I mean by this in just a second. And then we look at, well, the sum over sigma and f of this thing squared. Okay, so if you'd like, the example Philippe described here is kind of roughly of this nature. It's a little more complicated because it involves a quadratic extension, but there's a split analog of this that is quite closely related to this family here. Okay, so that's one example. So maybe a better example would be, so let's just say by example of a dyadic family, you could mean you take sigma to be absolute value to the IT, where t ranges over an interval that is dyadic. So meaning numbers between, say, some number and twice that number rather than something shorter than that. And so in that case, what this ends up becoming is like a second moment of the L function attached to pi. So to give a further specialization, you can take pi to be a suitable Eisenstein series with trivial parameters, and then this ends up just becoming the fourth moment of the zeta function. So this is an old example where we now have kind of many ways to treat this and its generalizations like we have here. But okay, for example, we don't know how to generalize something like this yet to any similar case involving, say, some higher degree general linear group here and some analogous one here of lower rank than the first one, subject to the conditions that we've outlined, where we want like, okay, we want a convexity critical moment, we want an asymptotic evaluation, and we also want it to be robust. So namely, we want a structured main term and an error term that is kind of a power of the conductor smaller than the main term. Although if you're willing to kind of assume some kind of recent advances, so let's say recent plus maybe let's say potential advances in homogeneous dynamics. So by like Lindenstrass, Einsiedler, Mohammadi, Wang, and maybe other people. So maybe one can get an analog for GLN plus 1 and GLN of this example. But at the moment, we don't have that, I think, fully available. And so in the body of the lecture, I'll kind of revisit this example in the simplest case from a couple of different perspectives. So revisiting what Philippe did. And yeah, you have a question? Oh, okay, what would the analogous family be for like numbers between t and 2t? Yeah, so yeah, that's a good question. So in this case, let's say sigma is on GLN, as it should be. So sigma, I mean, under some conditions, sigma you can describe its representation at infinity by some tuple of typically real numbers t1 through tn. And so then the analogous condition might be that, let's say, each tj lies between, well, you could do between t and 2t, but you might want to allow them to kind of vary simultaneously and maybe be kind of spread out in general position. So take a bunch of large numbers that are all of similar size, but are maybe a little bit far apart from each other, and then ask that each of the parameters be in some interval like that. That would be an example. Does that answer your question? Yeah, okay, yeah, okay. If you know the language of infinitesimal characters, you could say you take a kind of a ball in infinitesimal character space and then rescale it by the factor of t. So that would be a more concise way to say this. Yep. I mean, I'll just say while I'm finishing erasing that, like, you know, another example of what I mean by a dyadic family would be you take all of the Dirichlet characters of conductor Q. That's another basic example. So we saw literally that example treated in Philippe's lecture, and I'll revisit that here, also from a slightly different perspective. Okay, but continuing this kind of laundry list of examples just to kind of give an umbrella overview of how the methods that we have today break down. So we could also fix sigma on GL1 and vary pi on GL2 in a, what I'll call, short family. And then, so you could say sum over pi on GL2, or sorry, pi in F. Like so. And so here I don't think there are any examples in Philippe's lecture that were of this sort, where you summed over the GL2 thing. Did I remember correctly? Okay. So there are many examples, for instance, on the exercise sheet where we listed these references. So there's this paper of Ivanić Sarnak, which can be understood in this context. There is this paper of Ivanić on the spectral growth of automorphic L functions that's in this example, that's of this nature. And there are many more. Maybe I won't write down the complete laundry list because it'll get extremely long, especially if we think about families as generally as we have here. I should say what I mean by short here would be, so if we use the notation from above, it might mean that we consider, rather than dyadic intervals, we consider intervals each of length roughly 1. Or I guess Philippe spent some time talking about holomorphic modular forms of given weight. And another example of a short family would be you fix a weight, or you take the weight to be very large, but you take an individual weight, and you look at the modular forms at that weight. That would be a short family. Okay, so this has been done in many examples for GL2 and GL1, or I guess GL1 and GL2. And also, it's been generalized in many cases now to GLN and GLN plus 1. So this is maybe the method, okay, barring kind of more dynamics advances, that has seen kind of the most generalization to higher rank. So I have some papers. So I guess what started it was there's a paper of Blomer and Buttkane for the case of GL3. And then there's also a paper of Simon Marshall doing something kind of like this. And then, yeah, I have a few papers, and then I also have a paper with Yuki Hu. And then just to kind of, so I've mentioned Ivanic-Sarnak. So I'll write Ivanic, and by this I mean there's a paper on spectral growth of automorphic L functions. If you can't find the paper I'm referring to, just ask me. And then suitably interpreted, there are many other papers. There's a paper of Bykovsky. There's some papers of Blomer and Harkosh. So there are these papers by Fouvry, Kowalski, and Michel treating the same thing for trace weights. So this class of examples has been studied in many cases. And maybe I've forgotten some cases here, but okay. So I should say, okay, if we have these two methods, and they can treat kind of things on general GLN, why do we want or need any other methods? Like, what's the point of continuing this list here? So one argument would be that these, well, okay, you could argue in terms of, say, whether these methods give the best qualitative bounds, so they don't in all cases. We'll mention a fourth method here that gives better qualitative bounds. But another reason is that there are many examples where these methods don't give any good bound at all. So the issue lies in, I mean, if we go back to the first blackboard that I've now erased, there's this relation between the family size and the conductor that needs to hold in order for these moments to actually be what I called convexity critical. Namely, we recall we want to have the family size being roughly the fourth root of the total analytic conductor. And so that happens in these examples in some sense generically, but not 100% of the time. So I kind of want us to get us to a point where we can kind of dig our teeth into some like methodology rather than just summarizing what we know and don't know. But I'll just say, like, as a kind of remark here, so these two moments 1 and 2, the ones we have on the blackboards right now, are convexity critical. So i.e., the family size is at most q, I guess here we're doing to the 2 quarter minus delta, only if the pair pi sigma does not, let's say, experience, maybe this is a bit of a loaded verb for what's happening here, does not experience what's called conductor dropping. So conductor dropping means, if you look at the formula that defines the analytic conductor for this thing, it'll typically be a product over some number of quantities, the number being the degree, and you want each factor in that product to have roughly the same size as all the other factors. So if you're in that situation, then these turn out to be convexity critical. If you're not in that situation, so if you're in the case where any one of the parameters is much smaller than the others, then you're not, and these methods become useless. So I'll come back to that a bit later and write down what I just said, but just to kind of advertise in advance the shortcoming of these ones. Okay, so then another class of methods comes from the following fact. So if pi in some sense comes from an automorphic form on some odd special orthogonal group, so then there's this result of Lapide and Rallis. So it's known in the case that I'm, so you know, for like SO3, it's due to Walsh-Burget. So that's kind of the relevant case here, that L of pi half is non-negative. So in this situation, one can take, in these basic moment identities, k to be, well, not an integer, so that the moment involves an even integer, but you can take k to be a half integer. So you're allowed odd-powered moments and without the absolute value, because you don't need to put absolute values in if you already know the thing is real, and you don't need to take an even power if you already know that the thing is non-negative. So, so for short families on PGL2, so say F, so there are examples where we know how to estimate essentially sharply from above this moment here. And so what'll typically happen here is that the family size is roughly comparable to the conductor. So in particular, it's much smaller than the fourth root. Sorry, what am I saying? That doesn't look correct. Now I guess the family size is roughly the conductor to the half. Yeah. So then, so this of course has total conductor q cubed, and so q to the half is smaller than the fourth root of that total conductor, q to the 3/4. So you're actually in a situation where you're kind of well beyond the edge case for these family size and conductor, and you're going to prove without introducing an amplifier a strong subconvex bound. If you can get an estimate like this, so this implies that L of pi half is bounded by, so okay, q to the quarter is the trivial bound, and you can do better than that by the fraction 1/3. So this is, I think Philippe mentioned this. This is this Weil type savings. So this is, yeah, I guess this is, originally, so there are papers of Ivic and Connery Ivanic treating certain examples of this nature, and then there are a couple papers of Petro and Young treating more general examples, and then there have also been various papers kind of revisiting these from different methods. So I wrote one or two. There's a paper by Han Wu, by Wu, Furlenkov, and Balkanova. Yeah, and I imagine more papers being written generalizing this. So yeah, so this is another method. It doesn't apply in these conductor drop-in cases. So again, it's not something that gives you new subconvex bounds, but it's one of the methods for giving better bounds than what one gets by amplification. And also, it's interesting in that it's a method that you can use to bound even L functions attached to Dirichlet characters or the Riemann zeta function on GL1 by taking pi to be an Eisenstein series on GL2. So this is a method that I think it's fair to say, Kevin, I hope you'll correct me if I'm wrong, hasn't really been generalized to higher degree yet. So I've tossed around occasionally over the years. I mean, kind of what's happening here is one is using that PGL2 as like an SO3, and you could imagine more generally trying to do something for, say, SO5 or SO7 or SO9. And so I've had a sketch that I've been throwing around for the past 6 years or so, where you could try to generalize that maybe somehow, but the analysis again seems difficult. It's not clear to how to actually evaluate the geometric expressions that one gets when one tries to do that. So far this again seems to be a method that's kind of specific to this example. But it's an interesting one again for two reasons, because it involves non-negative L functions that are raised to an odd power, where you can actually do the analysis. And also it's an example where you can bound things on a lower degree group like GL1 by embedding them in an Eisenstein series on a higher degree group like PGL2. Okay, so I wasn't going to say anything further about that example, but I just wanted to mention it because it's an interesting and it's also a pretty accessible one. You can read these papers. But I will come back to examples 1, 2, and then the fourth one that I'm going to mention now. But yeah, any questions on these ones so far? While I erase. Yeah.
So in the second example, they are varying 5 on GL2. I assume the J varies as 1 and 2. And the short family.
Yeah, J would be like 1 and 2. Yeah.
We
Exactly.
are associating a pair of numbers for every 5, right?
Yeah, sure.
How are we associating a pair for every 5?
So I guess, for the purpose of the exposition, I was appealing to the same black box that I did in answering the other question about how do we group things on GLN. But, so for example, if you have Moss forms, so you're familiar with Moss forms. So they have an eigenvalue that looks like a quarter plus t squared. And so the way you associate a pair of numbers to that would be you take the numbers t and negative t, which are the parameters that define the induced representation underlying the Moss form. So then you'd ask that t and negative t both be in intervals of length 1, which is not so different from asking that t be in some interval of length 1. So one example would be you take Moss forms where t lies in an interval of length 1. Another example, the one that I mentioned out loud, is you just take all holomorphic forms whose weight is equal to some given integer k, where maybe k is very large. Yeah, we're assuming that t's are kind of tending off to infinity. They're kind of our main parameter. We're trying to use that to understand what?
We're trying to use that to understand the small to understand that everything on GL1.
Okay, so, sorry, I'm not sure I understand. So which example are we talking about? 2 or 3 or 1 or? 2 or 3. Can we choose one? Well, I guess for both of them, they're short families, yeah, okay. So in both of them, we choose short families, but then I think you asked the question, we're using them to study GL1. Okay, so I think your question is in more detail, how do we study GL1 using PGL2? Can we understand it like that, or? I mean, I think it just takes a couple seconds to answer it maybe in a basic form, which is just that, so for instance, this cubic moment up there, if you choose the family, all right, well, I ruined the erasing job because, anyway. All right, well, so that cubic moment above, let's say we choose the family to consist of one particular all Moss forms where the parameter lowercase t is in one of these short intervals, so say between capital T and capital T plus 1. So among the Moss forms, there are in particular the Eisenstein series. So you get the Eisenstein series with parameter t between capital T and capital T plus 1. And when pi is one of those Eisenstein series, this cubed of L function is just the 6th power of the Riemann zeta function. So now hopefully I'll get the water out and I won't get distracted, but so that cubic moment there will bound from above the 6th power of the Riemann zeta function over a very short interval. Okay, so now that I've erased, I'll just kind of write what I said. Yeah, sure. Oh. So okay, again, by short family, so for example, F, let's take it to contain Moss forms with eigenvalue quarter plus t squared, where t lies between capital T and capital T plus 1. So maybe we call that FT for emphasis. And so this contains in particular the Eisenstein series ET, provided that T is in this interval. And for this guy, the L function at 1/2 cubed is just the 6th power of the zeta function. So this moment contains the integral of the zeta function to the 6th power in magnitude over a short interval. So you're kind of compensating for the fact that it would basically be, I mean, it's already an open problem to estimate the zeta function 6th moment over a dyadic interval. And when the family gets smaller, the moment difficulty typically gets larger. So kind of doing this directly over a very short interval would maybe be a hopeless problem, but by thinking of this as the contribution to something involving automorphic forms of higher rank and a larger family there, it somehow becomes accessible. All right, does that answer our questions at all? All right. Anything else? All right, so the fourth method I'll highlight, which is kind of, I mean, in some sense a critical one, right? Because I've mentioned this, this conductor dropping problem, which shows up in the first two methods. And so you can't use those methods anytime one of the parameters is much smaller than the other. So this fourth method is kind of the one method that we know of that lets us get around that limitation. But unfortunately, we only know how to use this method when the group is GL2. So it uses special features of that case that we don't know how to get around. So, but okay, what is the family in a basic example? So it might be you take a sum over F So pi in, let's say, family F. So maybe on GL2, and you take the fourth power of the L function. That would be one kind of class of examples. Where now it's a bit tricky to kind of say whether the family should be thought of as short or long. We'll just treat some examples where we'll kind of see what we mean in cases. So maybe the simplest way to describe it is we take a conductor truncated family with given central character. So again, we'll illustrate what this means in some concrete examples. But the idea is that the kind of size of the family as you naively measure it will be short if the central character is ramified and long if the central character is unramified. But this gives a uniform description. So, or the other thing you could take is, well, a sum in the same sense, but maybe you take a Rencontres convolution like so, where pi prime is also on GL2. I assume that clock is accurate. Yeah. No, it's not. Okay. You can either take it to be fixed or you can let it vary simultaneously. Kind of both are fair game, but maybe taking it to be fixed is a good first step. Okay, so this comes up in papers of Duke, Fraley, and Ravanic. So for example, the last two in the papers in the bounds for automorphic L function series. So, so Philippe has a paper kind of treating this case in many examples. And then there's also the papers of so Venkatesh and then Michelle Venkatesh that kind of revisit this from another perspective. And so for example, the fact that we know how to do subconvexity for GL2 in general, it kind of like the key examples all follow from this method, which thus far is specific to GL2. Okay, so now with kind of the remaining time, I thought I would illustrate 1, 2, and 4 in kind of the most basic examples and showing how they look from a couple different perspectives. So I don't know if that's a lot to keep track of, right? We have like, 3 kind of families of moments that we're gonna illustrate, and then we're gonna kind of talk about them from a few different sides. But I hope that, gives some kind of structure for where we're going. All right, so let's start with an example of the first family of moments. So what we'll do is we'll fix f on GL2. So you could take it to be a modular form, a cusp form on, say, SL2Z. And let's look at, let's let Q go to infinity, maybe over the prime numbers. And let's look at the sum over all Dirichlet characters modulo Q of L of f times chi 1/2 squared. So this is something that Philippe already treated in his lecture, but I thought it wouldn't hurt to kind of just repeat it a bit. And you can think of this again as kind of like something closely related to the fourth moment of the zeta function. If you took chi not to be a Dirichlet character, but instead to be absolute value to the IT in a dyadic interval, and you took f to be an Eisenstein series, this would literally be the fourth moment. So it's some kind of cousin of that. Okay, so of course this is something that, you know, the approximate functional equation gives you a rough formula for. So I'll say, I'll ignore the kind of secondary term that we mentioned on the right board. So it's a sum over n of size roughly the square root of the conductor. So the conductor in this example, as Philippe explained, so in general, when you twist on GLN, the conductor becomes q to the n. Here n is 2. So the square root of the conductor in this case would be roughly q. And maybe, you know, for the purpose of thinking about subconvexity, we just focus on the main dyadic range where n is roughly of size q, because the smaller dyadic ranges, as we indicated over here, will contribute less. And then, okay, maybe we normalize the moment because we're interested in then showing that what we've written is bounded by 1 or is actually asymptotic to maybe 1 plus some robust error term. Okay, so then what does this expand to? Well, it becomes, I guess, a sum over m and n of lambda of m, lambda of n bar over square root of mn. So m and n are both of size q. And then an average over chi modulo q of chi of m, chi bar of n. And so this sum here, so I've kind of, I've been a little sloppy here. I've ignored the difference between, so maybe we really want to sum here over chi that are primitive of conductor q. So there should be an asterisk here to indicate primitivity, as well as here. But at least if, let's say, q is prime, this will kind of introduce a lower order modification. And so this sum then will detect something like the condition that m and n are congruent to each other modulo q. And hence this sum will, well, okay, this denominator will just have size q. So this will be something like 1 over q times the sum over m and n of size comparable to q and congruent to each other modulo q of lambda of m, lambda of n bar. So already from what we've written here, it's very easy to see that this sum is bounded above by something like 1. But okay, we remember the main goal was to prove kind of a structured asymptotic formula for something like this. So given that I think it's now 10:29, maybe we won't dive into that now, but okay, we can have the break, and if you'd like, you could look at the notes from Philippe's lecture to remind yourself of how that went. I mean, we'll kind of review it here anyway. But then, yeah, we'll pick up from there. We'll kind of understand this example in a couple different ways, and then we'll proceed to the other examples. Okay, thanks.